Hello, and welcome to New Scientist Weekly, your curated selection of the week's science stories. I'm Christy Taylor in New York.
And I'm Timothy Revel in London. This week, we've got mining nickel with a field of flowers, quantum Wi-Fi, time zones on the moon, a trip to the Arctic. We've got it all.
And Tim, you didn't even say the part where we've got ants that perform amputations. Truly everything. But first, this week, our reporter in Australia, James Woodford, has covered two extraordinary stories about ancient humans in caves. Both are about research that goes to the very heart of what makes us unique as a species. The first is about what may well be the world's oldest ritual, and the second is the world's oldest figurative rock art, and possibly the earliest evidence of storytelling. Welcome, James. Can you tell us, first of all, about that oldest ritual I just mentioned? I'm so curious about what we're talking about.
Yeah, it's an amazing story. I think when a lot of people nowadays think about rituals, maybe it's singing happy birthday or playing scissors, paper, rock in order to resolve who gets to sit on the window side of a plane or some other new craze on TikTok. But a team of Australian researchers has just announced the discovery of archaeological evidence suggesting that one ritual in the southeast of the continent here may have existed continuously for up to 12,000 years.
That is an incredible statement, and I'm wondering how anyone could possibly prove that?
That's exactly what I thought when I first saw this paper. I spoke to the researchers, and I have to say, they definitely convinced me, and other experts that I spoke to also agreed that this was an extraordinary bit of investigative scientific sleuthing. Basically, between 2019 and 2020, a team of archaeologists led by Bruno David at Monash University in Melbourne and members of a local Indigenous community called the Gunai Kurnai from southeastern Australia conducted an excavation at Clogs Cave, which is near the Snowy River in Victoria. And in the cave, when they conducted their excavation, they found two wooden sticks and also two really small ceremonial fireplaces. And when these sticks were dated, it turned out that they were 12,000 years old. And it was also clear that these sticks were artifacts that had been worked by humans, but the whole thing was really mysterious. Even so, it would have been a big story on its own, as they are among the oldest timber artifacts that have ever been found in Australia.
That's incredible. And, as we've hinted, there's definitely a but or an and in here, right?
Yeah, there really is. This is the kicker of this story, and that is that it gets really interesting because analysis of the timber showed two things. First, that the wood was from a casuarina tree, and secondly, the sticks were smeared with human or animal fats, and the residue of this still remained. And now the story goes from the interesting to the almost spooky.
Ooh.
Yeah, because at the same time as these archaeological discoveries were being made, the researchers were combing through an ethnographic report that was prepared in the 19th century by government geologist and anthropologist Alfred Howitt. Now, he was researching the customs and traditions of tribes in southeastern Australia in the 1880s. And in 1887, very close to Clogs Cave, he recorded the practices of Indigenous and what he called, so in quotation marks, wizards, now referred to as Mulla Malung, who are powerful Gunai Kurnai medicine men and women. He wrote a detailed account of one ceremony that involved smearing animal or human fat on throwing sticks made of casuarina wood and then placing them in small ceremonial fires as a magic charm or curse. And he understood that the ritual was to be used against an enemy or someone whom those conducting the ritual wished to harm. And back in the 19th century, Howitt wrote, and again, this is in quotations, "The wizard has, during this time, been singing his charm as it is usually expressed. He sings the man's name, and when the stick falls, The charm is complete. The practice still exists. So this is directly from his recordings at the time. Everyone is now convinced that there is just no other possible explanation for such a coincidence to be just chance, and that in fact, Howard was describing a ceremony that archaeologists have now established existed continuously for at least 12,000 years.
So, in other words, those 12,000-year-old sticks from the casuarina tree were for the same ritual that Howard saw performed in the year 1887. So, you've blown my mind a bit here. What about the other cave discovery announced this week?
This other story is pretty extraordinary too. This time, we're a bit further north on the Indonesian island of Sulawesi, where another team of Australian and Indonesian archaeologists has been studying a number of rock art sites using a new dating technique. In 2019, in the limestone caves of Maras, Pangkep, scientists dated art to approximately 44,000 years ago. At that time, that was already thought to be the oldest figurative rock art in the world and the oldest evidence of storytelling. However, using the new dating method, the team has shown that the site that made news in 2019 is actually at least 4,000 years older than thought 5 years ago. And then at a nearby site called Liang Karampuang, rock art has been dated to at least 51,200 years ago, so even older. And these paintings depict human-like figures interacting with a pig, and the site is now considered, in the researchers' words, the earliest known surviving example of representational art and visual storytelling in the world.
I love that it's about a pig, too. James, you're making me feel a bit impressed with our own species. We are so defined by art and ritual, but it's also becoming clear that this has been true about us for a very long time. So is there more we can learn from this art about the people who made it?
Look, even though the researchers have been studying these caves in Sulawesi for a long time now, really the story is just unfolding in such a fascinating way. And so, yeah, there sure is so much more we can learn, Christy. The scientists believe that it is possible that whoever painted this art may have been among the earliest migrants that came through those regions, and possibly the same first wave of modern people who are on their way to inhabit the Australian continent. So, yeah, this story is going to have a lot more installments to come.
Now, we've got another James with us. Reporter James Deneen is here, and as you may remember, he was on with us earlier this year to talk about researchers trying to mine for rare earth elements using seaweed. The logic is it's a more sustainable source of metals needed for a bunch of clean energy technologies. And James, you're back this week to tell us about another story of this kind, mining for nickel using flowers. James, what's going on with this one?
Yes, so much like with the seaweed, the idea behind phytomining or agromining, as this mining with plants is sometimes called, is to grow species of plants that accumulate high concentrations of certain metals from soil. Then you can harvest the plants and extract and purify the metals. This is not a new idea. Researchers have been at it for decades, and these hyperaccumulator plants have been used in all sorts of projects to clean up soils contaminated with metals. But now the rising demand for metals and minerals key to clean energy technologies like EV batteries and wind turbines has governments and companies in search of all sorts of new sources, and ideally sources that avoid destructive conventional mining. And one of those sources could be plants.
And so you've been speaking to some companies about this, but those that are specifically focusing on using plants to mine for nickel. You just tell us a bit about that. Why is nickel so important?
Well, nickel is a key component of many EV batteries and things like stainless steel. We now use more than 3 million tons of the stuff each year, and demand is forecast to double in the next 2 decades. But mining and refining nickel is environmentally destructive and emissions intensive. currently producing a ton of nickel now generates between 10 and 59 tons of CO2 emissions, depending on how it's mined and refined. So there's an interest in finding greener sources of the metal. And there's also been quite a bit of research on species of plants known to accumulate high concentrations of nickel, up to around 2% of their biomass in some cases. So unlike with the seaweed, which was at an even earlier stage of research and development, we actually know that it is feasible to mine for nickel with plants.
It's feasible, it's appealing, it feels a little magic or science fiction-y. Have companies actually started to mine for nickel with plants, though?
Yes, they've started doing it, but only at a very small scale. One is a French company called Econic that told me they have 100 hectares of nickel accumulating plants under cultivation in the Baltics, with some plans to expand their operations in Malaysia. My story, though, this week mainly focused on a newer company called Metal Plant that just completed its largest harvest yet on a few hectares at its nickel farm in Albania. They're focused on Albania because the mantle rocks that make up the country's mountains have generated soil that's fairly rich in nickel. And many of the species native to Albania are also tolerant to these nickel soils that would be toxic to a lot of other types of plants. The company is working with a species called Odontaria decipiens, which is a shrub that has these distinctive yellow flowers.
This sounds like it could also be one of the prettiest mines on the planet. I'm just thinking bushes and yellow flowers all over the place.
Yeah, the yellow flowers stand out really strikingly against the green valley. We have some photos of it online. What's really interesting about this company, though, is that they are also trying a new approach to phytomining by combining it with a method of removing CO2 from the atmosphere by spreading large volumes of rock dust on the farm. This is called enhanced rock weathering. And the idea is to use the rock dust both to remove CO2 as well as replenish supplies of nickel in the soil as it's taken up by the plants. Should be said, getting that rock dust would still require mining a quarry, but the result could be a source of carbon negative nickel that avoids more damaging approaches to mining. And if such phytomining efforts were to scale up to tens of thousands of hectares, they could conceivably meet a small fraction of nickel demand. But no one really sees phytomining really competing with conventional mining. It's more of a greener alternative.
Next up, we're going wireless. Quantum wireless, that is. Or, as I like to say, quireless. And that could get us to greater levels of data security than anything ever seen before. Physics reporter Carmela Padovich-Callahan is here to talk about the latest in quantum communication. Carmela, what is this device exactly, and how did we make Wi-Fi quantum?
Right. So this week I reported on a chip that could make it possible to transmit and receive quantum signals through what physicists would call free space, but you and I would probably call air, sort of quantum communication without any wires. The idea is that you would take this chip and integrate it with whatever other quantum device you have already. So maybe your quantum computer or maybe some sort of a sensor. And the chip would then enable this other device to receive quantum information, just like your phone does when you use regular wireless.
Got it. So I take it we could use technology like this to create a large quantum communication network the same way we have this, massive system of wireless devices and signals in a more conventional way. But why do we want that?
Yeah, I mean, this is a great question, right? So this would be an enabling technology, but why do we need it to begin with? The simplest motivation for building this sort of global quantum communication network, and sort of actually this is the same motivation people have for building smaller networks that already exist, is that with quantum signals, there's a really good chance of everything being virtually unhackable. This is because quantum information is much, much harder to surreptitiously copy than classical information. Quantum cryptography protocols are also much harder to break than whatever we use now. So if you think about, something mundane like using your phone to check your bank account, this is something that you're doing wirelessly. And if you could go quantum, if you and your bank could both go quantum, now this wireless interaction would be much safer from hackers and other sort of nefarious actors.
Go quantum is such a good line, such a great call to action. As you kind of hinted, there are quite a few cities around the world already that have their own small quantum communication networks, but they tend to be using optical fibers, actual cables, rather than anything wireless. But there's also been some wireless quantum communication before, but in kind of extreme cases like between satellites or between drones. So with this new thing, what's really new?
Yeah, I think the sort of big standout point is that this is a standalone device, that it's miniaturized, that it's compact, that it's on chip. So, you could make it the same way we make other silicon-based chips. We sort of have the groundwork for that. And the thing that you make doesn't actually need anything super special. You don't have to keep it in a giant fridge, which is often the case with quantum devices. And it has like 1,000 components crammed onto it, including 32 tiny antennas, which can be controlled pretty precisely, and they can pick up signals. They're coming from different directions. They can screen out signals that are coming from different directions. And once they pick up, a noisy quantum signal, the antennas can kind of work together to do a little bit of processing and get a better signal, or sort of convert it into something you could feed into another quantum device. So this chip is giving you practicality, and it's giving you versatility, and it's not requiring you that you buy, dark fiber in the city or something like that. So there's a lot of room for this device to really sort of bring Wi-Fi capability to a whole swath of quantum things.
Okay, so there's lots of could in there. How close are we to this actually being an option?
Right. I mean, this is always the question, and it's unfortunately always also really hard to predict the future. But I did speak to someone, a researcher, who told me that sort of if these chips could be sort of reliably good at transmitting information a few meters apart from each other, we could, in the next 5-10 years, have something like indoor quantum encryption that's done wirelessly. So again, maybe you're in a bank or something like that. And there's also another sort of a possibility for growth here, which is that you could use these sort of wireless functionality to connect together two quantum computers to make a bigger quantum computer. And we are always trying to make bigger quantum computers because that would make them more powerful. So if people who are super invested, sort of big industry players who are super invested in bigger and bigger quantum computers, if they sort of got interested in this wireless functionality, that could probably speed up the field quite a bit. So I think the future for this is bright, but it's hard to put a precise number on it.
I'm so excited to log on to my Quamputer and use some wireless.
Yeah, we need to come up with a way to put it on the phone, really, because then I can go on quantum TikTok with my quantum wireless.
Quick quack? No.
Yeah.
It's time for a quick break. If you're eager to update your musical playlists, this week's Culture Lab is one big symphonic treat. Columnist Bethan Ackerley interviews composer David Ibbett, who's crafted an entire symphony using sonifications of data from Mars. That's already in your feed, wherever you get what you're listening to right now.
Today's global supply chains are labyrinthine, and that makes them hard to understand and hard to control. This is an issue because many companies are trying to make their supply chains more sustainable, more resilient, and at the same time, more profitable. Find out about the approaches and technologies that are beginning to emerge to help companies achieve this in our New Scientist Collab feature sponsored by PwC UK that takes you inside the supply chain revolution. Available at newscientist.com/PwC.
All right, our own Rowan Hooper is freshly back from 80 degrees north in the high Arctic, where he spent time in the Svalbard archipelago on a New Scientist discovery tour. He has sent us this report from his travels, which included a chat about the soil science of that icy realm.
All right, I've got myself wrapped up in a dry suit. So I've got thermals on and then zipped up into a dry suit with seals on the feet and wrists and neck. So I'm completely protected against the elements. It's about 0 to 1 degrees above freezing. And I'm on the water in the Arctic in a kayak. And ahead of me, there's these huge cliffs and what looked like a swarm of, like you see a swarm of insects far ahead. And I'm going to go and find out what they are. All right, I'm here with Peter Wainwright. He's guiding us here today. But Peter, tell us where we are, because I don't think I've done a more unusual location.
We're at a place called Alkafjellet on the northeast side of Spitsbergen in the Hinloppen Strait. And it's a mesmerizing place. It's not the biggest Brunix guillemot colony, but it's one of the most impressive because we can actually get really close to it along the water's edge. It's these dramatic 100-meter high dolerite cliffs that come straight down into the water's edge, and the birds are nesting just meters above the sea level, and we're paddling right along the edge of these cliffs.
And it's quite a pungent smell of the guano here, and you can see actually where it's fertilized a lot of the sort of more level bits of the cliffs, and there's moss and soils built up, which some of the gulls are collecting for their nests. But it's like being in a swarm here. They're just flying in and out. There's kittiwakes, glaucous gulls over there. They're predators, right?
They are, yeah. So they're probably hunting. They're probably looking for eggs, or maybe the young chicks. And here the chicks are maybe a little less vulnerable, but if the brunette guillemots are nesting a little bit further back, and the chicks will have to walk a little bit before taking the plunge to begin their adult life, then they're more vulnerable to the glaucous gulls. But yeah, the gulls are definitely soaring around trying to take advantage of whatever they can.
It's absolutely amazing to be in the center of all this, and to get here on kayaks as well. It's really beautiful. Some of it sounds like laughter, doesn't it? Evil laughter. That's about the clearest I've ever heard them say kittiwake, kittiwake. So we just paddled on a bit now from the colony. If you heard me making funny noises a little bit, that was because of the quite overpowering smell of the guano, real ammonia smell. But now we've come out to the face of quite a big glacier, and it really makes me doubt whether we can really engineer any solutions to holding back glacial melt. And obviously we always say the real thing we have to do is reduce emissions and remove carbon we've already put in the atmosphere. But there are so many plans and startups thinking about ways to save glaciers directly. But when you see one like this close up, you just think, how on earth can you stop that physically? Now, I'm back from Svalbard now, and I'm still thinking a lot about the glaciers I saw, which were so much more vast and awesome than when you see them on TV or in photos, and actually really poignant to see them. They were carving into the sea and almost retreating before our eyes. But that's definitely not anecdotal. This week, there was a study in Nature Communications that found that the speed of decline of more than 1,000 glaciers in the Juneau ice field in North America, that's more than doubled in recent decades. And in Svalbard, I was also interested in the soil formation in areas that have been exposed as glaciers disappear. And coincidentally, this week also sees the publication of a paper looking at just that. And to tell us about this is author James Bradley of Queen Mary University in London. James, thanks for joining us. Now, we know the Arctic is warming like 6 or 7 times faster than the rest of the world. And you've been working up there for 10 years. You must have seen a massive change, even in 10 years, have you?
Yeah, so the glacier that's the study of this paper and its full field, 10 years ago, I was walking around on its surface and taking samples of the ice surface, drilling with an ice corer into the surface. And some of the areas where we were working on the ice now have now disappeared, and we're left with kind of barren soils.
So in this latest work, you've been sampling the land that's exposed as the glacier retreats. So what have you found?
So what's been known is that into older soils, you have more accumulation of carbon, increased amounts of plant life that become visible. But what we didn't know already is how those microbial colonizers, the first organisms that can become established in the soil, how they kind of engineer the soil in order to be able to store that carbon and build up that carbon.
Are there sort of bacteria just lying dormant under it when it's ice, and they kind of spring into action when the ice retreats? And so how do they start fixing carbon in soil, in this proto soil?
So what we have is 2 very different ecosystems. We have the environment underneath the ice before it's melted and retreated away, and then we have this kind of proglacial soil landscape. What we know now is that even the frozen landscape underneath the ice is an active microbial ecosystem. And these microbes there get their energy not from sunlight, but from the crushed up rock and water that's bringing nutrients and other sources of energy down into this kind of dark subglacial environment. And then when that ice retreats, all of a sudden you have light and you have a connectivity to the atmosphere. So that connectivity brings energy, but it also brings a source of microbes that might be deposited from the atmosphere or deposited from snowmelt. And these microbes can get a foothold into this soil and start building up stocks of organic matter and nutrients, for example, by fixing carbon or nitrogen from the atmosphere, or from stabilizing carbon that might be deposited as it's kind of falling out of the sky.
And what about the fungal component to this microbial action? Tell us about that.
What we can see in that soils close to the glacier front that are dominated by fungi, they're more efficient at using that carbon for growth and less for respiration. And then further away from the glacier, we have soils that are dominated by bacteria, and they're cycling that carbon much more rapidly, and they're respiring a lot more of that carbon. So what this is telling us is that the fungi in particular are important kind of ecosystem engineers, because when they assimilate or when they take up organic carbon that is available kind of externally in the soil, they're very efficient at stabilizing that into biomass compared to the bacteria that might incorporate the same amount of carbon, but they respire a lot of it back to CO2 in the atmosphere.
I don't suppose we can make this fungi a white species of fungi to increase the albedo and, make up for all the loss of ice, can we?
Yeah, the particular sort of genus or taxa of fungi that we see that are very important in this process are black yeasts.
Yeah.
And you see these little patches of soils that are becoming sort of colonized, and you tend to see these little green colonies and these little black colonies. And then over time, that leads to mosses and kind of flowering plants over timescales of decades. But the albedo is a big, important question, sort of the reflectivity of the environment. But what's actually important is that these are very seasonal environments. And this is kind of where the work is going next, is to understand the seasonal dynamics. But for at least half of the year, these soils are covered in snow. So at least for the spring period, when the light returns, there is a huge amount of solar radiation that is reflected back into the atmosphere. A lot of that incoming energy and incoming light is reflected because we have a snow-covered landscape until around June. And then when that snow retreats, we're left with the bare exposed glacier ice and the bare soil.
That was Rowan Hooper speaking with Arctic biogeochemist James Bradley of Queen Mary University of London.
Christy, we've talked a lot about the amazing things that animals do on this podcast, but I've got another one for you. It's the first non-human animal that performs medical amputations.
Ooh, what's the animal? I know we talked about chimps tending wounds just a few weeks ago, so are amputations another cool primate trick?
That was very primate normative of you there. No, the amputators in question are actually ants. Just a common carpenter ant that a researcher saw chewing off a nestmate's wounded leg one day.
As you do.
Yeah. Many species of ants, they already perform a kind of wound care where they secrete this specialized antimicrobial substance that can treat infections. But these carpenter ants, they don't have these antimicrobials. Instead, they just kind of remove troubled limbs.
So as you said, this was one ant that a researcher saw one day. Were they able to find more evidence that this is, a practice as opposed to a one-off, or maybe like that ant got confused about who its friends really were?
Yeah, I'll bite your leg off. No, they did actually find lots of evidence of this. So after this chance observation, the team looked at video footage of the ants, and they observed that ants performed these amputations pretty regularly. And each amputation, they seem to take about 6 minutes. So it's not an accidental thing, not a stray chomp. It's a real operation in some ways. And on top of that, the team, they ran an experiment where they gave several dozen ants both leg injuries and infections, and then tested what happened when only some got amputations. And the group that got amputations had a 90% lower mortality rate than the control group. So all of this suggests that by performing amputations, carpenter ants are preventing pathogens from spreading and improving the survival of their nestmates.
All right, Tim, I've got a fun story for you. Let's say you wanted to give the moon a time zone.
Well, we don't need to say that because I would like to give the moon a time zone. How would we go about doing that?
Well, this is exactly what the U.S. has asked NASA to do. They are supposed to come up with a coordinated lunar time zone called LTC. I am not exactly sure why this is up to the U.S. to decide, but that's what's happening right now. And the only complication is per general relativity, time moves just a bit faster on the moon than on Earth. This is because the moon's gravity is weaker, because it's smaller, and that leads to a phenomenon called time dilation. So time stretches out just a little bit compared to time here.
Yeah, I guess I'm aware of this in the abstract, but like practically speaking, how much of a difference are we talking about?
It's not too bad. It's only about 57.5 microseconds per Earth day. So let's say an astronaut spent 50 years living on the moon continuously. They'd be around 1 second older than if they'd stayed on Earth for that time.
Okay, so not that noticeable for a person. So why does this actually matter for creating this coordinated lunar time zone?
Right. So at the end of the day, having very accurate clocks for the moon's flow of time will be important not just for keeping track of that occasional extra second, but maybe more importantly, in helping people navigate the surface. So our GPS systems on Earth track time down to the nanosecond. That's even more precise. That's 1,000th of a microsecond. And so if we're asking humans on the moon to navigate dangerous terrain or otherwise find their way accurately, especially maybe on the far side of the moon where communication is even harder, they'll need very precise timekeeping to keep them safe. But if nations can agree to at least stick to the same understanding of how lunar time works compared to Earth's, we can also establish a kind of 0 day when the tracking of that time zone begins. And ideally, we'll put some atomic clocks on the moon to actually monitor the time dilation as it happens from that day forward.
Yeah, it's such a small time it seems kind of irrelevant, but then we know that satellites that we use for GPS, they've got to account for this already. That's something that happens every single day. All right, if you've got leftover eggshells from your lunch ramen, might I suggest a cool new medical use for them?
I mean, currently I use them as medicine for my houseplants, which need calcium sometimes, but go on.
Yeah, that's a good one. I've done that before myself too. One other option is you could use them to help form a scaffold to regrow broken bones.
Okay, how does that work? I mean, I broke my leg once and it regrew fine without any help.
Yeah, well, I'm glad to hear that. But sometimes there are situations where people need a bit more help. Their bones aren't growing fast enough or they just won't regrow naturally. And under normal circumstances, bones are growing using a kind of scaffold called the extracellular matrix. And it's this jelly-like material that sits between your cells and supports bone growth, both physically and chemically. Now, artificial scaffolds can help in cases where natural regeneration isn't going well, but the thing is those scaffolds are sometimes rejected or they cause complications.
Is this where the eggshells come in? And by eggshells, do we really mean chicken eggs?
Yeah, it is actually chicken eggs. So a research team has done some testing using scaffolds with different amounts of crushed up eggshells, chicken eggshells, and then those are mixed up with a kind of moldable plastic. They then inserted a kind of precursor to bone-growing cells into the scaffolds and measured the results after 2 weeks. And at least some of the scaffolds they made, well, they worked, and they had encouraged the cells to begin to mature into cells that can produce bone material. Now, the researchers say it's possible this works so well because eggshells already contain some of the actual materials that exist in bone, the calcium that you mentioned as one of them. And so using them can trick the body into categorizing that scaffold as part of itself. That's it for this week. If you like this show and think more people should know about us, please give us a 5-star rating or even a review on Spotify and Apple Podcasts.
We've got more fascinating stories from New Scientist on our website at newscientist.com. Tell your friends, write about it on a cave 50,000 years ago. We'll be back next week. Bye for now.
Bye.
This podcast is produced by OG Podcasts. Find out more at ogpodcasts.co.uk.